Okay, we now discuss about cable subjected to a uniform distributed load, which is commonly the case for suspension bridges or even cable stay bridge and pedestrian bridges that are carrying their own weight. For suspension bridges, usually the weight of the cable is oftentimes neglected because they are quite small compared to the weight of the bridge and the weight of the vehicles passing through the bridge. So cables provide a very effective means of supporting the dead weight of girders or bridge decks having very long spans. It traverses wide and long in our local bridges. We do not usually have these suspension bridges, but this is common, especially in those areas where they are spanning large bodies of water, like in the United States, in Japan, and in Europe. Oftentimes, because the bridge is quite costly, so these suspension bridges are quite that covers or spans very long distances, and worldwide it is the bridge in Japan. Presently, it is the bridge in Japan which holds the record for longest span bridge. Okay, now a suspension bridge is commonly provided with from the cables. We have the hangers. From the main cable, the hangers are the ones carrying directly the load from the bridge deck, and it's the main cable that transmits that load to the piers or the towers, as we also call this. And it's the bridge deck that carries the load of the cable, all the load of the vehicles passing through the bridge. And then we have here the main cables. So these are the important components of a suspension bridge. And as our analysis will proceed, when the cable transmits the load from the bridge deck, the load is distributed in terms of the weights of the girders, weight of the slabs, whatever is the material used. Oftentimes they are made of steel girders with concrete on top, concrete slab. So it's the main tower that will be supporting the weight from the cable, and the weight of the cable, of course, or what is being supported by the main cable, are the weight from the hangers that carries the load from the bridge deck. Some cases are pedestrian bridges. Pedestrian bridges do not behave like suspension bridge, because oftentimes pedestrian bridges are carrying pedestrians, and oftentimes they are significantly analyzed with the load distributed along the length of the bridge. So the distribution therefore is transmitted by the cable along the span, or along the arc length, along its total length. So it's different from the suspension bridge, because suspension bridge, the loading is uniform. No, it is computed from from the application of the distributed load along its horizontal span. While pedestrian bridges, the loading is distributed along the actual length of the pedestrian. So this is how we analyze cables used for pedestrian bridges. This is also similar to cables on electric wiring, electric cables, also being supported by towers. So the distribution of the load is also similar to the pedestrian bridges. That the load is significantly taken from the lead load of the cable, and it is distributed along the length of the cable, which follows the either parabolic or whatever the curve is followed by the cable. So these cables, which form different geometric shapes, we have the curve that is followed by a suspension bridge is parabola, while that of the pedestrian bridge is catenary. Pedestrian bridges and cables for electric purposes. And what is the significant difference between two? By determining whether it's a parabola or catenary is quite important, because the analysis of the forces carried by the cable is largely dependent on the type of curve, or the type of the structure itself, because they have different reactions to the applied loadings. So if we have to analyze first the parabolic cable, we represent the supports to be plane connected, and then the cable will have its lowest point at the 0, 0 XY axis. So the load is distributed uniformly, and to derive the equations for the behavior of the curve, let us consider a certain infinitesimal length, small length, from the origin. So our origin here is the lowest point of the parabola, and we have this portion of the cable where we have here T sub O, the tension of the cable at the lowest point, and maximum T could be located at the supports. And along the span of the cable from the zero or the origin towards the support, we have there the distribution of T inclined at an angle of alpha, and we can describe the slope or the differential distances, vertical and horizontal, y and x, with this applied load W, which is, if you notice, it is distributed along the horizontal length of the cable. So from this diagram, we can now sum forces along x equals 0, and we have P times the cosine of alpha along the horizontal should be equal to P sub O, the tension forces. And the transmission force along y equals 0, it will be, this load is resisted by the vertical component of T. T sine alpha is equal to W times x. T sub O will not have any effect on the vertical summation of forces. And then we divide the second equation by the first equation. T sine alpha equals Wx divided by T cosine alpha equals T sub O. So that sine alpha and cosine alpha becomes tangent alpha, and then T over T will be cancelled. So we'll have the result, tangent alpha is Wx divided by T sub O. And we take the derivative because tangent alpha is simply the slope of the line, a slope of the curve, the slope at the tangent line, tangent at any points along the curve from the origin or from the 0 point, the lowest point of the parabola to the supports. So this is described as the slope of the tangent line along any point. Tangent alpha is dy dx, and then we integrate dy with respect to x. We also integrate the right side, similar as the previous integral of dy dx. dy dx is equal to w times x divided by t squared. And the result of this is y is equal to w times x squared. We integrate the x dx is x squared. N plus 1 divided by n plus 1. So it's x squared divided by 2 t sub o plus c. So we have here a constant of integration c, and that is to be determined in accordance with the boundary conditions of our of the curve of the keyboard. And this c is computed from considering the origin at the lowest point at x equals 0, y is also 0. So x equals 0, y equals 0, and it gives us c equals 0, because if we substitute x equals 0 here and 0, c therefore is also 0. And so if we have now the value of c, we go back to the equation for y. Y is equal to w over 2 times t sub o times x squared, and that is an equation of a parabola. Okay, so this proves that the different points along the cable is described by a parabola. The distance y from the origin, y is equal to w over 2 t sub o times x squared. Okay, so we'll go now to the catenary, or for pre-strand bridges or cables in towers, electrical towers. The distribution of the load is along the total length, distributed along the arc. So similarly, we'll do analysis on infinitesimal length. This time S is quite important because it is there where we have to distribute the load. And so from here we do the same. Some forces along x equals 0, and we will have along the horizontal direction w will not have any effect. So it's also t cosine alpha equals to t sub o. Along the y direction we will have t sine alpha w times s. Okay, so it's different. For parabola it is w times x, so this times w times s. And also dividing the second equation by the first equation, t sine alpha is ws, t cosine alpha is also again tangent alpha. This will be cancelled, so tangent alpha is ws divided by 2. W times s divided by 2. So from here, the same dy dx is ws over t sub o, and then this dy dx actually is taken from the slope of the tangent at any point. We have dy and dx. The hypotenuse is ds, and from this triangle, which is right triangle, we can just solve for ds by Pythagorean theorem. ds squared, or the hypotenuse squared, is equal to the sum of the squares of the two legs. d squared is equal to x squared plus dy squared, and then ds is equal to the square root of dx squared plus dy squared. And we have now, if we take the second derivative of this equation, dy dx over w, that is equal to ws over t sub o. Second derivative dy dx. So we will take the derivative of Ws over T sub O times dx, divided by dx. And we'll get this one is d squared y over dx squared is equal to W over S, W over T sub O, because W and T sub O are constants. And we take ds over dx. And this is because ds is this one. We just substitute ds for that value of square root of dx squared plus dy squared. So this is now the equation that we have to take that integral twice. And the result, you just can review this from your integral calculus. And the result now is W over T sub O square root of 1 plus dy over dx squared. And we simply say integral, taking the integral right side equation gives us this transcendental equation, which is not a parabola. There is no or the variable is not is only carrying an exponent of 1. So this is an equation that represents a catenary. A catenary which is different from our previous parabola. So here we are demonstrating the difference between structure that is carrying a load distributed along its span and structure in which the load is distributed along its actual length, along the arc of the cable. So for suspension bridges, then the behavior of the variation of the cable or the curve is a parabola, while that of the pedestrian bridge, it is described by a catenary. Okay, so it now depends on the type of distribution of the load that we can differentiate one from the other. Okay, in the book by Hibbeler, you just try to read the derivation as presented by Hibbeler. It's just the same, but he is only presenting us the derivation of parabola, that he takes only 1/2 of the span of the cable, and then the horizontal distance is equivalent to L. Now, so you have to take note of this, because once you have to analyze the whole span, you might be using the whole span as the value of L in your derivation for the value of Y, but it's not. It should be 1/2, because the derivation presented by Hibbeler is only 1/2 of the span of the cable. So from the lowest point to the support. So L there should be 1/2 to the span. Or if the supports are not at the same level, then L is the distance from the lowest point to the support, lowest point and to the other support. And they might vary, because if they are not located at the same level, then the distance between the supports and the origin, or Y0, would be different. They are only equal if the cable, the supports of the cable are at the same level, the same vertical elevation. Okay, so this is the equations that Hibbeler is giving us. Y is equal to W O over 2 if H times X. It's similar to what we had derived also for suspension bridge parabolic. And then if H is the horizontal force, this is equal to T sub O in our derivation, WO times L squared over 2H. Then we have also Y is equal to H over L squared times X squared. This describes the equation considering the parabola. Okay, so this is just for this one. If it depends on what are the variable given. So in terms of the configuration of the suspension bridge, then we can just do the determination of Y based from the different distances, or we can solve for Y based from the forces or the applied loading W and the corresponding effect on the tension at the horizontal direction. Then we have Tmax usually at the supports. Maximum tension is at supports equivalent to the square root of H squared and WO times L squared. So it's the total force corresponding to the components. Along the horizontal is H, along the vertical is W times L squared. Again, remember L is the distance from the origin to the support. Then we have Tmax could be from our derivation also, it's WO times L square root of 1 plus L over 2H squared. So you can just use these equations directly because there are problems that could easily be solved or directly could be solved based from the given forces or applied loadings, distances. But the problem with using directly the equations is that you may not be able to remember, or sometimes we will miss some of the terms in the formula. So we can just do statistical procedure, meaning depending on the configuration of our brains. So we can just apply the statics of bodies, rigid bodies, so that we can analyze the cable with uniform loading without depending so much on the formulas, on the equations. Pero if you have a sharp memory, then you can just directly use the equations in the solution of problems. So let's consider this problem so that we can apply the equations. And we may have an alternate equation for this because again, it's more easy to remember the statistical procedure, especially so because we can apply the equations of equilibrium, that we can determine those forces that will balance the different forces developed as well as the applied loadings on the bridge or on the suspension cable. So the cable will break when the maximum tension reaches Tmax of 5,000 kilonewtons, meaning this is the maximum amount of force that we can apply so that the cable is stable, will not break. Determine the maximum uniform distributed W, the distributed W along the horizontal distribution. So our solution will start with using the equations. So the Tmax is equal to W, so the maximum load that could be carried, which is 5,000 kilonewtons, should be equal to WO times L divided times the square root of 1 plus L over 2H squared. So since the variables most or the force, maximum force given, the length is known from the figure, and then we have H is also given, we can just simply apply the given variables to the equation of Tmax. In which case, we will have W times 50 meters length. Remember, the total length is 100 meters, so the length to be used in this equation is 1/2 of the, because the supports are on the same level and the curve is symmetrical. Then square root of 1 plus L 50 divided by 2 times H. H is the distance from the lowest point to the support, to the supporting tower or where it is connected. So it's 12 meters given, and it's to be squared. The result, or Tmax is 5,000 is given, and then we have W is 43.273 kilonewtons per meter. That's the uniform load on the cable. Okay, so this is what I was telling a while ago, that we can directly solve for the variable from the given data. directly from the equation that we formulated. But we can also do this using the statics of rigid bodies, or applying the principles of equilibrium. You can just formulate equations based from equilibrium and the corresponding directions of the forces that will develop in the supports. So from the whole structure, we can have the equations, the reactions. Here we have EY and EX at the joint B, BY, BX. And then we can just have the summation of moment at B, or we can also use A, point A, but in this case we have summation moment at B equals 0, so that we can solve for EY. And we have EY, which will cause clockwise moment at joint B. It is negative because it's opposite the designated positive direction of the moment. Its moment arm is 100 meters from joint B, and then we have W distributed in a span of 100, and its moment arm distance from the center to point B, 1/2 of the span. So there's only one unknown here. EY could be expressed in W because the main unknown value is W, the distributed load. So we express EY in terms of W, 100 W over 2. 100 times 100 divided by 2 is 100 W divided by 100, so the 100 W divided by 2. Then summation force on Y equals 0. Of course, we have EY plus BY is equal to the distributed load. EY plus BY minus W times 100 was 0. And we will have the equation BY is W times 100 because EY is known. 100 W total load minus EY, 100 W over 2. And we will also get that BY equals 100 W over 2, they are equal. So this is just to show that EY should be equal to BY to resist the total load. Then we'll take 1/2 of the span, from where the derivation also made by Euler in determining the different variables. Considering our span here, 50 meters, then we have our horizontal force at this point. W times 50 is applied at the center because it's uniformly distributed load, so it's the total load should be acting at the center. And here we have summation of moment at B equals 0. At this point, we have if h times the distance, 12 meters, it is negative because it will have capacity moment while this will have positive. So 50W times 25, 50W times 25, which is the moment of the distributed load, is positive, and then minus if h times 12, so that we can have if h is equal to 50 times 25 divided by 12, or 104.167 W. And considering the direction of the forces and the total Tmax, the three forces could be represented in a closed polygon. It's much simpler to analyze forces in a polygon because it represents a triangular closed diagram. That is, we can just do or apply the Pythagorean theorem that the square of the hypotenuse is equal to the sum of the squares of the two legs. So the Tmax squared is equal to By squared plus B sub x squared. From that, we will have our of course our Tmax is known or given. We first sum forces along x equals 0, and we will have Bx minus if h equals 0. There are no other forces along the horizontal, so Bx and Fh. And then Bx should be equal to Fh, where Fh is 104.167 W. Okay. So that we can substitute this into the equation for Tmax squared. So from here, from this equation, we can just substitute the given Tmax. Dy is 50W, and then we have dx also squared. Then we will have simplifying. We just take the square of the different terms, and this is now the equation. From here we can solve for W, 43.273, and if you have to recall first computation for W, okay, 43.273, they are equal. So most problems actually do not necessarily have only one equation, one solution, because we could just apply different possibilities, and in here our equations of equilibrium would be very necessary in giving us an alternate solution to this problem. We have here another example which represents a typical cable that carries a span, single span or bridge, and this could be the wheel loads passing through the bridge. Okay, so this actually is an actual representation of the application of the loads, and then supported by the hangers to the main cable, and the spacing between hangers is also given in 2 meters. The support at A is pin, meaning hinge support or pin connected, and at C is a rocker, so this will only have a vertical reaction, 0 horizontal, and this will have vertical and horizontal reactions. Okay, so the cable has a parabolic shape, so we are given the configuration of the cable, which is a parabola. We are required to draw the shear and moment diagrams. This is a problem actually given by Hebeler. The problem before this is to determine the forces, tension in cable. But this problem is solely for the drawing of shear moment diagram. So if you solve this problem, then you actually will be solving for the two problems as given by the book by Hebeler. So we start here with the determination of the reaction using the whole cable or the whole structure as a free body. Then we will have the forces at B is dy, the horizontal is the force Fh. Then at E we have Ey and Fh, meaning the horizontal force is constant throughout the different points along the cable. Ex for horizontal reaction at A, and Ey for B, Cx and Cy at point C. So from here we some moment at point C equals 0 to solve for or to express Ey and Dy. So we have minus Ey times 16 moment arm for Ey from point C. 1, 2, 3, 4, 5, 6, 7, 8. 8 times 2 is 16. So also with Ey, we are similarly located vertically, horizontally. The horizontal distance is the same. Then we have 3 kilonewtons times this moment arm. 16 minus 4 is 12. and minus 5 times 6. That equation will give us one of the required equations. So we will designate this as our equation number 1. In order that we can solve this one, because there are two unknowns, so AY and EY. So we will separate one half of the structure from the other segment. So we consider first the left segment. For the left segment is a sum moment at joint B equals 0, so that we can have the second equation that relates AY with DY, and that equation should be AY times 8, 1, 2, 3, 4 times 2. So from here, AY times 8, this is also negative because it's clockwise, and minus dy times 8 also. Then we have now the if it's here, another if it's at point F. So if it's times 12, 9 plus 3 is 12, then minus if it's times this distance, which is 9. If it's here is positive, while if it's here is negative. And then plus, we have the applied load here of 3 kilonewtons times 4. So we have another equation of AY and BY, and this will be our equation number 2. And in equation number 1, it's also AY plus DY, equivalent to a certain coefficient or constant. So we just equate equation 1 and equation 2. From where we have 4.125 is equal to 1.5 plus 0.375 if it's, and this will give us our if it's equal to 7 kilonewtons. These are equal if it's along any point. The horizontal force is equal. So and we substitute this to the equation W equals to if it's times h over L squared. So 2 times 7 times 3, this vertical distance of the origin or the lowest point to the location of if it's at the maximum. And we will have W 0.65625 kilonewtons per meter, kilonewtons per meter. And we will have here now equation for Tmax, W times L square root of 1 plus L over 2A squared, and we get Tmax equals 8.75 kilonewtons. And for the hanger, since the hanger is distributed or is placed 2 meters apart, so that each hanger will have 2 times WO, okay? They carry this amount of W sub O times 2 meters. So each hanger will have to carry 1.3125 kilonewtons. Okay, each hanger distributed 2 meters from each other. So with these forces now known, then we have submission moment at C equals 0, and we will get the value of EY times the forces distributed to sa hangers. The hanger is we have EY times 16 plus 3 times 12 plus 5 times 6, then minus the distributed load from the hangers. We have 14 and moment arms, okay, add lang to moment arms times the load on the hanger equals 0, and we will get AY equals minus 46875 kilonewton. And so since our EY and assumed direction is upward, the result is negative, therefore it should be downward. Okay, once the result of our value from the assumed direction is negative, then it should be the opposite of this direction, so this should be downward. Then submission moment at A equals 0 to solve for CY. We will do also determining or applying the known forces in the hangers. CY times 16 minus 3 times 4 with arm of 3, then 5 times 10 minus the hangers, the load of the hangers, 14 with the arms from point A. Then we will get the value of CY is minus 718, also downward, meaning Again, because CY is assumed to be directed upward, but the result is negative, so it should be downward. So we now draw the shear moment diagrams.